Hello, everybody. Hello. Welcome to the Astronomy Club meeting. It's good to see everybody here. First order of business. Those of you that signed up for eyepiece observing this Friday that have already talked to Kevin or have signed up the sheet for Kevin, we are going to meet in the South Stewart parking lot at 4:30 this Friday, and a few just kind of things. Food will be provided. That means pizza, snacks, whatever the grant provides. If you have a car, bring it so that you can drive people up. We'll probably have more than enough cars, so you might just carpool with someone else. And the plan is to go up to the top of the mountain, to the Mount Leonard Sky Center, and socialize with grad students if you met Wayne, and just have a fun time while Nat's students use the 61-inch telescope until 11 p.m. and then we get it until and then we just observe it. We just do some observing until we feel like we're done. And then we plan on driving down the mountain that night. If you really want to stay up there overnight, we can probably arrange that, but I think it would just be better if we drove down that night because we don't have to deal with stuff. But if you really want to, we can. And Kevin wanted me to mention that if you are going on this trip, we need you to pay dues in order to cover some of the cost. So if you have not paid dues, pay dues, and we can get you.
The cost of the trip is semester dues.
And this is people observing eyepieces sometimes.
I got that too.
So, and then, not this Saturday, but the Saturday after that is October 1st. It's the first Saturday of the month. We have our Sabino Canyon Star Party. Again, there's a football game that day, so we're going to meet in the park, by the park around what? I looked on.
There's any games in October.
Like there's one this week.
No, there's not one until later.
Okay. I looked at the calendar late last night, so maybe, it might have been a away game. That would make sense. So we're going to meet in the South, disregard this. We're going to meet in the South Stewart parking lot then, which is just over there at 4:30, and we will just go over there and do our Sabino Canyon Star Party. Some other interesting things coming up. In the past we've done kind of outreach for Biosphere 2 as part of our Science Saturdays series, and basically go to the biosphere. We do some outreach where they have like all kinds of people coming through, and we did liquid nitrogen ones, we did meteor craters, all kind of, like where you throw a rock at a piece of sand and you see the crater it makes. And they've really liked us coming there. They've had nothing but positive things to say, and so we're just going to continue doing this. We have 2 events scheduled for this semester so far. Probably going to be all of it scheduled for this semester. It's October 22nd and November 19th, and there'll be more information about that as they approach. But basically, you go there from 11 to 2. We meet here beforehand, and you go get some coffee, and then carpool to the biosphere is a little bit away. And one of the big incentives is you get a free tour of Biosphere 2, which is just a really cool place if you've never been. And so that's something that we have coming up. Also, Kevin and CT went to the last TAAA meeting and kind of talked to them about being involved in with the Astronomy Club, and from what I heard, they were really excited about it. So I'm kind of thinking that it can work that we help them set up dark skies and help them out with different events and stuff, and they can help us out with some of our events that we might need help with, and they also have a lot of advertising power, so they could like advertise for our Sabina Canyon Star parties, and they could get a lot of people to come. Does that sound like something people want to do? Yes. Okay. As I mentioned, if you want to go on the Star Party this Friday, you have to pay dues, but if you want to really do a lot of other things that we're going to do this semester, you'll have to pay dues eventually, so it's a good idea just to pay dues. It's $10 a semester, and also it really helps if you fill out this membership form, but I'm assuming that by this point a lot of you already have. So I know my email went out a little bit late, but today we're going to have Camber talk about her research at the BLA she did over the summer. And so if you're really impressed and you want to do a research talk at the Astronomy Club, talk to me after the meeting. Last thing to mention, we have all our projects going on. The Exoplanet project, it's at Mondays at 5:30. After the telescope projects, Tuesdays at 5:30, and outreach materials is going to become important as we get closer to the Biosphere 2 dates, because we're going to need to create some new outreach materials that we can show the Biosphere people as we get closer to the dates. So we're going to need to towards the end of, after we're done with everything else, I'm going to kind of set up a sign-up sheet so that you can, if you're interested in making some outreach materials, you can kind of indicate when you want to meet for that. And finally, radio project, Thursdays, 5:05 at 5:05. We are not meeting this Thursday. That's correct. Okay, so without further ado, yes, TT. Oh yes, yes. Go for it.
So Teacher Play has a dark side near sun sites, depending on which you're out, and they're having a grand opening star party for the second phase of the dark side. And they've got quite a few telescopes that are already down there and are available for use if you want to go down there. I'm going down Saturday. I'm headed down, so if anyone wants to grab that opportunity. Really great skies, and it's not a 61-inch flight. The skies are simply the best skies I've ever seen. Plus, you don't have to like
Yeah. Talk to CT if you're interested in dark sky observing this Saturday. So without further ado, I'll turn it over to Camber, who's going to talk about water masers in star-forming regions at large. Yes.
Okay, so this summer I did an REU internship at the National Radio Astronomy Observatory, and I was at their Socorro, New Mexico location. And Socorro is where everything for the Very Large Array is run, which isn't actually in Socorro. It's a little bit more in the middle of nowhere, which you can see from the picture. And but my project didn't have anything to do with the day the Imperials requisitioned the control center in order to intercept the signal from the Rebel Alliance. So instead, I worked with Jürgen Ott and David Meyer on a project looking for water masers in star-forming regions of the Large Magellanic Cloud. And then Mark Clausen, who's a water maser expert, also helped us when we had no idea what was going on. So what the heck's a maser? So masers are stimulated emission. It's the exact same thing as a laser, except at longer wavelengths. And the way masers and lasers work is that you get some sort of radiation coming in, and it's absorbed by an electron in a low energy state of an atom. It goes up to a high energy state, quickly decays to a slightly lower energy state, and then you get a photon whose energy is the same as the energy difference between this state and the ground state, and it agitates the electron up here, causing it to jump to the ground state and emit a photon, so you get one photon in and two photons out. And then another thing that's important, especially for astronomical masers, is that you need to have velocity coherence. And that means that all the atoms need to be at more, or molecules need to be at more or less the same velocity, so that a photon emitted from one has an energy that's close enough to the correct energy in the rest frame of another electron to cause more emission. So masers in space, some common ones that you get are masers in hydroxide, silicon monoxide, water, and methanol. And you see masers in star-forming regions around young stellar objects, which are protostars and premium sequence stars. You see them around evolved stars, such as asymptotic giant branch stars. You see them around planetary nebula, supernova remnants, and AGN. Water masers emit at 22,235 megahertz, and most of the water masers that we know of are in our own galaxy. So that's half the title, and the other half of the title is in the Large Magellanic Cloud. So the LMC is an irregular galaxy. It's one of the satellite galaxies for the Milky Way, and it's about 50 kiloparsecs away, so it's the same distance as some parts of our own galaxy. It has a low metallicity when you compare it to the Milky Way, and a high UV flux, so it has different composition. And it's more or less face-on, which means you can look at a whole bunch of different parts of it. And then it interacts with the Milky Way and the SMC. And you can see evidence of this interaction, if there wasn't so much light in this room, from this pink right here, which is the Magellanic Stream with the LMC, the SMC, and the Milky Way. But the nature of this interaction is a little bit debatable. For a long time, we thought that the LMC was in a bound orbit around the Milky Way. And we think this because if you look at the star formation history of the LMC, you see periodic bursts of star formation, which line up with periodic bursts of star formation in our own galaxy. But in 2006, a study came out where people used the proper motions of stars to get the trajectory of the galaxy, and they found that it was moving way too fast to be in a bound orbit around the Milky Way, and it should only be on its first nearby pass, which goes in contradiction to the star formation history. So the initial motivation behind this project was to identify water masers that could be used in a separate proper motion study of the LMC and hopefully resolve this controversy. But when we got started on the project, we found that the masers were really interesting in and of themselves because they allowed us to compare star formation in the LMC with star formation in the Milky Way. So the observations for this were not done on the VLA, since the LMC is a southern source. They were done on the Australia Telescope Compact Array in 2007 and 2008, so obviously I didn't have any part in that. We had 37 different pointings, which are the red dots on this graph. And even though each one of our pointings looks like it contains a large section of the sky, we were nowhere near covering the entire LMC. So when the data got to me, it was reduced, which was awesome. And I just had to go through all of the data cubes and try and find the masers. And the data cubes that I first got looked like this one, where they were pretty noisy, and I was supposed to try to pick out peaks, but there's lots of things that look like peaks. So in order to keep from going completely insane, I applied a 5 sigma mask so that only emission that's above the 5 sigma noise level showed up. And if the resolution was better, you could see that on this one where the 5 sigma mask has been applied, you see only 2 dots, but they're there, really, they are. So that was great, because then I only had 2 dots in this particular frame instead of like 20. But I still needed a way to differentiate between actual masers and noise. And so to do that, I had to come up with some more criteria. And those were that I needed to have at least 3 pixels clustered together above the 5 sigma level. And then looking at the spectra, it had to be wider than 1 channel width. So these are examples of spectra that made the cut and that we're considering to be masers. And so after I went through and identified everything, I made up a bunch of maps that look like this. And what this is the background is 3.6 micron Spitzer data. This particular map is of 30 Doradus, which is the brightest star-forming region in the local group. And it's also where the largest known stars are. So the large circles are pointings. The contours are carbon monoxide. The crosses are the masers that I found. The small circles are young stellar objects. The triangles are evolved sources, such as AGB stars. And then these two squares are sources that we found to be near masers that didn't otherwise have a source near them. And we found them in the SAGE catalog, but there wasn't enough data on them for us to conclusively identify what type of object they were. They could, however, be YSOs. So going through all the different data cubes, I found 27 masers. 20 of them are, as far as I'm able to determine, new detections. 21 of the masers are associated with young stellar objects. 4 are associated with the unclassified SAGE objects. And 2 of them are unassociated with any of the different objects that we looked at. So for the YSOs in our field, we had a 9.8% detection rate of masers. And if you flip that around, at least 78% of the masers we detected are associated with YSOs. And if it turns out that these 4 objects that are unclassified are YSOs, then 93% of the masers we detected are associated with YSOs. So this shows the luminosity distribution of the detected masers, with most of them peaking between 10 to the minus 7 and 10 to the minus 6 solar luminosities. Our highest is at 10 to the minus 4. In comparison, the brightest known maser in our own galaxy is 1 solar luminosity. And then if we compare this to a distribution of masers around YSOs in our own galaxy, which is the dotted line on this graph, you notice that most of the masers peak up at about 10 to the negative 4, while we are between negative 7 and negative 6. So the masers that we're detecting in the LNC tend to be a lot fainter. So this is the magnitude distribution for the YSOs in our fields. And then the dotted line is the magnitude distribution for the YSOs with masers. And it's cut off, but we have 8th magnitude right about here, which is where most of our YSOs are. But the YSOs with masers tend to be a lot brighter. And that made us wonder whether or not maser strength and YSO brightness were related. So of course we graphed the two things against each other, and we stared at it, and we decided that was a really dumb way to figure out if there was a trend. So instead we fit a least squares fit to it, and we found that there does seem to be a correlation between maser strength and YSO brightness. However, we really feel like we should be detecting a lot more masers around the 8th magnitude. This sensitivity limit is actually a little bit high. It should be more down here. So we should be seeing YSOs with masers around here, and we're not, which is weird because there's lots of YSOs that are 8th magnitude. Yeah?
Error bars in this graph?
What?
If you put error bars within too small to see, or
Yeah, they'd be too small to see. And so it could be that there's some threshold magnitude above which you get mazing and below which you don't. It's interesting to note that this relationship is also seen in YSOs and masers in our own galaxy, but no one's really certain what causes this relationship. And then finally, this is a color magnitude diagram of the YSOs in our regions, with the red dots being the ones with masers. And this bottom axis has a 24 micron observations, and at 24 microns, you get dust absorbing less, and you also get dust emitting more. And since the YSOs with masers tend to be brighter at 24 microns, it could be that these YSOs tend to be more embedded than the other YSOs in our regions. So in conclusion, I found 27 masers, 20 of them were new, and most of them are around YSOs, which are probably the more embedded YSOs. And there is a weak correlation between YSO magnitude and maser luminosity, and that's what I did this summer.
So what do YSOs have to say about the history of star formation in the Magellanic Cloud and how it relates to its history? Does it speak to the fact that it's probably not a satellite, or it has a regular orbit, or just how does it inform them of the current ideas about that?
YSOs in and of themselves don't tell you anything about the history because all you know is they're young stars now. But masers, since they're bright point sources, are really good for measuring positions and how they change over time. So what you would do is you would just have a campaign where over a couple of years you observe the same masers and you see how much they move, and you observe masers in a bunch of different regions of the galaxy, and from that you get the dynamics of the galaxy.
So you're supplementing the research on the proper motions of the stars to see if that...
Right.
Okay, cool.
Yeah.
Yeah.
So what's the difference between like a water emission line and a maser when you look at the spectrum?
Masers tend to be brighter, and they also tend to be narrower because they're point sources, so you don't get the velocity dispersion that you would with just a regular emission line.
So when they decided that the LMC was not going to be the LMC, did they, are they saying it's a flyby kind of casting, or what is it?
I think it's like when two galaxies merge, and at first you get like just an initial pass by, and then it kind of turns around and comes back, and then you get orbiting. I think they're saying that it's something like that.
Oh.
And it pissed a lot of people off.
I believe it.